Hey, Chemsters, this is Mrs. Vandalay bringing you more Chemstar video. And this is the promised video of VSEPR. And along with VSEPR, we're going to talk about polarity. Okay, so you definitely will need your periodic table today and a pencil, definitely with an eraser today. So why don't you take a few moments and get those out. Okay, hopefully you have everything you need. So this phrase is super duper important, all right? So it says inorganic especially structure determines functions. This is why we need to know about Lewis dots and attractions. Attractions are based on polarity of the bonds and the molecules themselves. This will determine why certain things are gases and certain things are liquids, all right? It's because of structure determining function. So that's why we need to determine polarity, okay? And we're going to determine that by looking at the geometry, okay? So first of all, let's talk about ionic, polar, and nonpolar bonds. They're based on the electronegativity difference. So what is electronegativity real quick? It's the measure of an atom's attractions to electrons, okay? It ranges from 0.1 to 4.0. The highest values, all right, means the most attraction. And a guy named, oh gosh, I forgot who it was now. I'm drawing a blank. But anyway, some guy came up with this, okay? These are man-made numbers, if you will, okay? So he took fluorine, which was the most attractive to an electron, if you will, and he said, let's call it a 4. And then he based everything else on fluorine. Now, why a 4, might you ask? Here's a little tidbit. This is why I wish I remembered his name. That was his golf handicap. So he must have been a pretty good golfer, all right, to have a 4.0 handicap. So anyway, that's where it came from. So how then do we determine? We take the electronegativity, what difference? We're going to subtract these two values, okay? So then based on that difference, we're going to determine if it's polar, nonpolar, or ionic. So let's kind of scroll down a little bit. Okay, so what are my ranges? If I subtract, it goes from 0 to 0.4. All right, it is considered nonpolar. There is not going to be anything between 0.4 and 0.5. So if it's between 0.5 and 1.7, it's polar. And then if it's between 1.8 and beyond, it's ionic. Well, guess what? We're not going to talk about ionic too much here, okay? We're going to find out organic is mostly in this range, okay? We're not going to be dealing with elements that are going to subtract. You have such a big number, okay? So it says in organic, we'll primarily deal with carbon, hydrogen, oxygen, nitrogen, and the halogens. Which ones are the halogens? That's your group 17. So now go to that periodic table. Hopefully the one I gave you has these electronegativities on them. And let's determine which elements listed above will form a non-polar bond with carbon. So here I have these, all right, and I know I don't have the whole period here. I can scrub a little bit, I suppose. There we go. And now carbon is 2.5. So the question is, 2.5 minus what was going to give me that 0.4? And the answer is 2.1, I believe. So anything that I talked about, so C, H, N, O, and then all these guys, which one are going to give me a 0.4 or less? Well, let's try this. What's 2.5 minus 2.1? Oh, that's 0.4. All right, so I'd put that on the list. About 2.5 and 3.0, subtract those, you get 0.5. That's polar. About 3.5 minus 2.5, that's 1.0. That's polar. How about 4.0 minus 2.5? That's polar. What about 3.0 minus 2.5? That's polar. About 2.8 minus 2.5? That's 0.3. Hey, that's nonpolar. How about 2.5 minus 2.5? That's 0. That is nonpolar. And if you even want to include astatine, which I don't think we're ever going to talk about astatine, but that would also be nonpolar. So let's go back to our notes. So which elements listed above, C, H, O, N, or the halogens, will form a nonpolar bond with carbon? Well, this is probably the most important one here, C and H, okay? That was a nonpolar bond. Now, if you want to include these two, that's fine. I didn't even write the astatine one, but we really don't talk a lot about this. All right, this is huge. So which ones formed a polar bond with carbon? Definitely the oxygen, definitely the nitrogen, definitely the fluorine, and definitely the chlorine. Okay, that's important. Keep that in mind. So which elements listed above will form an ionic bond? None. We rarely talk about ionic compounds in organic. Why? Because carbon and the elements we talk about will not form an ionic bond. All right. So we're not going to talk about francium and carbon. We have no reason to. Okay. So what are my big four electronegativities? All right. The key elements to remember are NOFCl. Is that any coincidence that these are the same elements when bonded with carbon will give me a polar bond? And the answer is no, it is no coincidence. All right, so I will call these the big four. So those are the ones you need. So does that really mean you need a periodic table with you at all times? Not really. If it's not one of these, it's not going to be a polar bond. Okay, so get to know that. Now, someone in the past called these the No Friends Club, NOFCL. Why? Because they don't share nicely. All right, and that's what this electronegativity is all about, is how well do they share that pair of electrons, okay? So those in No Friends Club, they don't share very nice, okay? So there you go. So that's important. That is part one of our discussion. So part two of our discussion is VSEPR, is geometry. So get ready for that. Here's where you really need your eraser. All right, so here's our discussion about VSEPR. So we start with VSEPR and talk about, well, what is an electron group? All right, where are the electrons? Well, you have two possible places for electrons. You have lone pairs, and bonds, the actual bonds are added together. So when I ask about how many electron groups you have, I'm talking about how many lone pairs does a central atom have and how many bonds do you have, and you add that together. Okay, so I wrote note, double and triple bonds act like one unit. All right, because we're talking about geometry, we're talking about shape. Okay, and actually the running joke is VSEPR was the original example of social distancing, because these electrons want to be as far away from each other as possible. Okay, so what is the base shape for zero lone pairs? All right, oh, I'm sorry, for two electron groups. So here is this. It's a linear molecule, all right, with no lone pairs. Okay, like H and H, something like that. You have no lone pairs and you have two electron groups in a sense. Okay, so there's my linear. Three electron groups are going to look like, well, it's going to be trigonal planar. Hang on, let me scroll down a little bit more. All right, it's going to look like this. That's your trigonal planar. And then for four electron groups, you might remember this. This is what you'd call tetrahedral. And that would be 109 degrees away from each other. This is 120, and this is 180. So what if I have two electron groups with one lone pair? All right, that will work. Okay, so once again, it is linear. Oh, let me, yeah, here we go. Now what I kind of did is I kind of erased this, all right, and I have, it's still linear, you're not changing. But watch what happens when I look at some of these other ones, and in a sense, I'm going to erase, okay? So here is my original trigonal planar, the original three electron groups. But what happens if I erase that? And in its place, I'm going to put a lone pair. Ready? Jink. Now what? It's no longer a trigonal planar. These electrons are here, but I don't see the bonds, all right? It's going to be bent. And it's still about 120, maybe a little bit less, but close to 120, okay? Now watch what I do with this next one. So I'm going to start out with tetrahedral, all right? But I'm going to erase one of these, and I'm going to put in its lone pair. So I'm going to erase that, and in its place, I'm going to put a lone pair. So now what is the shape of this? It is trigonal pyramidal. And what happened? The angles went down from 109 to 107. These electron pairs are actually squeezing down those bonds just a little bit to be trigonal pyramidal. All right, so let's see what happens next when I have oops, sorry about that, when I have 2 lone pairs? Well, guess what? It's not going to exist here, okay? You're not going to have 2 electron groups with 2 lone pairs. It'd be an atom, all right? So it doesn't help us. So let's see what happens when I start here. So for each lone pair, I'm going to take away a bond because in its place, it's going to be a lone pair. So I had a lone pair here and a lone pair here. So now what is this shape? We'll just take a look at it and come up with, yeah, that's linear, okay? And finally, with the tetrahedral over here, what happens when I have 2 lone pairs? Let me bring this up. So what I'm going to do, I'm going to erase, I'm going to start off my tetrahedral, and I'm going to lose these 2 lines here. And why? Because in its place are my lone pairs, right? And what does that make it? We'll take a look. It is bent. But what's different about this bent, it's 104. The bent up here is 120 that started out as trigonal planar. But the one over here that started out as tetrahedral is now about 104. So these 2 lone pairs are still squeezing that down. Okay, what about 3 lone pair? Well, guess what? This doesn't exist. If I have 3 lone pairs, now you have an atom in a sense, so that doesn't help you. And so what do I do with this one? Well, how many bonds am I going to replace with lone pairs? 1, 2, 3. So in its place, I now have, let's see here, 1, 2, and 3. So what shape is that going to be? That's going to be linear. So hopefully this is a good review of your first year chemistry. If you recall, I could go on. All right, I could have 5 electron groups and 6 electron groups. Do you remember hearing about trigonal bipyramidal and octahedral and seesaw and all those folks? That doesn't apply for organic. We aren't going to worry about those, okay? It won't happen here. So these are the ones you need to know. So now what? Now we need to look at which shapes are symmetrical. Symmetrical, I'm looking at around the central atom. All right, now I am also assuming that all the atoms are the same around the central atom. All right, for right now. Okay, so let's kind of go back and look. So it's really easy if you have no lone pairs, folks. These are all symmetrical. They're all symmetrical. Okay, and what does that mean? That the bonds are equally pulling on that central atom. Okay, so those are symmetrical. So what if I have 1 lone pair? Well, again, I am assuming that each one of these things are the same. So this has the same element on both. These have the same elements on both, okay? Because then if you start talking like mixing and matching some elements, it's all going to depend on if it's a big 4 or not. So what am I going to do here? All right, so this could also be symmetrical, but now it's asymmetrical and asymmetrical. All right, again, assuming that I have the same element on there, okay? It's not always going to be the case. So folks, a lot of times this could be asymmetrical, all right? So you really got to be careful as to what elements we're talking about, okay? So over here, it's hard to have like linear with 2 lone pairs and have the same element. So we got to be careful. This could be symmetrical, but it also could be asymmetrical. All right. When you talk about linear, you got to, like I said, be really careful. But for this one, this is most often going to be asymmetrical. All right. And then down here, again, depending on what element it is, all right, it could be symmetrical or it could be asymmetrical. So that's when you're kind of like in that, well, which one is it, Mrs. Vanderwey? How am I supposed to know? It truly, with the linears, it truly depends on what 2 elements you're talking about, okay? All right, so hopefully by doing the next section, that this is going to clear up some of these things, all right? So why am I worried about the symmetry? It is important to determine if the whole molecule is polar or nonpolar, and it is that which will determine its function. Remember I said structure determines function? It's this right here, putting these 2 things together, the bonds and the symmetry, whether the molecule is polar or nonpolar. So this is huge. A polar molecule, you must have two conditions met. You must be polar and not symmetrical. All right, you must have polar bonds like the big four, and it can't be symmetrical. That means it's going to be bent, or it can be trigonal planar or trigonal pyramidal. All right, so you're looking at the symmetry and the bonds. Now, a nonpolar molecule will either have nonpolar bonds, which means there's no discussion. Now, if we have all carbons and hydrogens, okay, it's going to be nonpolar bonds, nonpolar molecule. But you could have a case where you have polar bonds, but perfectly symmetrical. That means those polar bonds cancels out. If you've taken physics, you might have heard about vectors. The vectors cancel out, so you have a net dipole of 0. How is that for some strange terminology? All right, but so that's how we have to look at both. So let's look at the next page. We're going to do some of these together. So let's look at HCN, all right? And I know I copied over where the name and the date stuff is. I put this here as a reminder of what our end goal is, all right? Is determine if the whole molecule is polar or nonpolar. So my first step is do the Lewis structure, all right? So what's my first step? I have to count my valence electrons. Go ahead and count them up. If you have that periodic table handy, how many valence electrons does HCN have? Go ahead and do that. Okay, hopefully you got 10. That's what I got. So carbon's my central atom. Anytime you see carbon, stick in the middle. Here's my nitrogen, and here's my hydrogen. So what's my next step here? Well, my next step is to go ahead and start putting these lone pairs around the non-central atom. All right, I've done that. And now count. I have 2, 4, 6, 8, 10. I've used up all my electrons. I don't have any left. Now what's up with this? Carbon has only 4 electrons. So what's going to happen? I'll go, hope you have your eraser. All right. I'm going to put, I'm going to put the lone pair that was here, and I can put the lone pair here. Oh, I have a triple bond, don't I? I have a triple bond. So I'm only going to look at your electron group, or I'm sorry, your essential atom to count how many electron groups I have. So right here, I have carbon. I have 1 unit of bonds, if you will, and another. So I have 2 electron groups here. Okay. And how many lone pairs are on the carbon? Well, folks, if it's organic, you should get 0. Carbon will never have lone pairs. Okay. Excuse me. So go back to the shape. What has 2 electron groups and no lone pairs on the central atom? We'll go back. It's right here. No lone pairs and 2 electron groups. What did we say? It is linear. So now what? Is it symmetrical or not? Well, if both of these, let's say, were hydrogen, or both of these were nitrogen, it would be symmetrical. But because the elements that are bonded to carbon on both sides are different, it is not symmetrical. Is there any polar bonds? Do you really have to do your subtraction? The answer is no. I see a big 4. What were our big 4? NOFCl. I see an N bonded to carbon. I already know that's a polar bond. So the question is this symmetrical or not? Well, it's not. Are my bonds polar or non-polar? They're polar. Look at here. I have polar bonds and not symmetrical. So guess what? This molecule is polar. And that's a big deal. Okay, let's look at SO2 next. So go ahead and count your electrons. I got 18. How about you? All right, so here's my sulfur, here's my oxygen, and here's another, whoops, and here's another oxygen. Sorry about that. And what do I need to do next? I need to add some lone pairs. All right, so I'm going to add lone pairs around the oxygen. And how many did I use? 2, 4, 6, 8, 10, 12, 14, 16. I got 2 more left. All right, I put on the central atom. Remember doing this? So now what? Oxygens are great, but what's wrong? Uh-oh, this is Van der Waals. Sulfur only has 6. So pick one of these. I'll pick one down here. And what am I going to do? I'm going to swing those around and make a double bond. Okay, So let's see how this works. So how many electron groups around sulfur? I have one bond unit, and one lone pair, so that's 3. Folks, this is not 4. So I'm starting off with some of these double and triple bonds, all right? I treat the double and triple bonds as a unit, all right? How many lone pairs are on sulfur? 1. So it starts off as trigonal planar. That's what this 3 does for me. But what happens? I erase one of those bonds and it becomes bent. So a better version of this would kind of look, I did put my double bond in, all right, would look this way. Now, folks, I'm using a keyboard, so this is not 120 degrees. I get it, all right? But if I could make my angles better, that would be about 120 degrees-ish, all right, here, okay? So that's my bent molecule. So is it symmetrical? Oh, no way, Jose. All right, definitely not. All right, it's bent. Your bents are not symmetrical. Do I have any polar bonds? Folks, I see a big 4. I see oxygen. All right, if you don't believe me, go back and look at that electronegativity chart and subtract, and you're going to find it is definitely a polar molecule. So is this, or a polar bond, so is this entire molecule polar? Yes, it is. I have my 2 requirements to be a polar molecule. Do you remember what those requirements are? Polar bonds, yep, we have an oxygen, and it is not symmetrical. Yes, it is bent, so it is a polar molecule. So what I'd like you to do next is go ahead and do NH3 on your own and see how you do. So pause this, come back, and see what you get. All right, hopefully you had a chance to do all this instead of just waiting for me. So this is what I got. I had 8 electrons. I put nitrogen in the middle, put the 3 hydrogens around it. I don't add any more electrons to hydrogen. Remember doing that? But I did that at 2, 4, 6, so I had to put a lone pair of nitrogen. So now what? I have 2, 4, 6, 8 electrons, worked out great. I have 4 electron groups. I have 3 bonds and 1 lone pair. Add those together, got 4, but one of them is a lone pair. So this becomes trigonal pyramidal. So it starts off as tetrahedral, erase a bond, put a lone pair in, and now I have a trigonal pyramidal. It is not symmetrical. I see a big 4, it's nitrogen, so the whole bond is polar. How about the next one? A little bit different here. Let's try NO3 next. All right, so here we go. I have NO3. I have 24 electrons. How did I get that? 5 plus 3 times 6 is 18. So 5 plus 18 is 23. But don't forget, I have to add that extra negative because it's the charge. All right, so I have 24 electrons. So here's my nitrogen, here's my oxygen, here's my oxygen, and here is my other oxygen, okay? So what do? Here we go. Did you do this too? I hope so. Now, what happened when I did all this? How many electrons have I used? 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24. All right, so that's good. But now what? Oh my goodness, Mrs. Vanderlooy, nitrogen didn't have enough, did it? So what do I need to do? I put an extra line here, okay? All right, so now because it's ionic, has an ion, I need to put brackets around it and the charge. I don't know if you remember doing that or not. So how many electron groups do I have? I have 1, 2, 3. Remember, this is 1 unit, so I have 3 electron groups. How many lone pairs do I have? None. Okay. What would that shape be? Trigonal planar. Is it symmetrical? Yes. If it doesn't have any lone pairs, it is going to be symmetrical. Now, what about my bonds? What's an NO bond? We didn't talk about that. Well, nitrogen's 3.0, hydrogen, or excuse me, oxygen's 3.0, nitrogen's 3, let's take it again. Oxygen's 3.5, nitrogen's 3.0, subtract, get 0.5, it's still polar. But look, this is our first case. It is symmetrical with polar bonds. What does that mean? Is it non-polar bonds? No. Is it symmetrical? Yes. So no matter what, because it is symmetrical, it is, oops, not polar, it is non-polar. All right, now this next one's a little bit different. And the reason being, I have two central atoms. I have two carbons. So I'm going to start off with this, and now I'm going to put 6 hydrogens around it. Are you following along? Hopefully you are. All right. And so this would be my structure with 6 hydrogens. By the way, how many valence electrons do I have? I have 8 plus 6 is 14. Well, do I have 14? Let's check this out. 2, 4, 6, 8, 10, 12, 14. I'm good. No lone pairs on carbon. Isn't that a good thing? Isn't carbon never supposed to have that? Correct. All right. Oops, sorry. That just popped up there. So because this is symmetrical in every way, all right, 4 bonds and 4 bonds. I have hydrogens all around here, all right. I'm just going to look at one of the carbons, all right. I'm going to show you on the next page a time when you shouldn't use, that idea, okay. So here I'm going to use one carbon. So what's true for this carbon is true for that carbon. And so I have no lone pairs. It is tetrahedral, perfectly symmetrical. What about the bonds? Well, we know that each CH bond is nonpolar, correct? We already learned that. What about the CC bond? You can't forget that one. Well, what is any number minus itself is 0. So all bonds are nonpolar. So this is a nonpolar molecule. So why don't you spend a few minutes and go ahead and do CH4 for me. Pause this. All right, welcome back. Hopefully you did this. And I'll put my 4 hydrogens around here. And here I go. Well, how many electrons do I get? I have 8 plus 4 is 12. How many did I use? 2, 4, 6, 8, 10. Hey, I got some extra electrons. So what am I going to do? I'm going to put a double bond here. Why do I make a double bond? Can any hydrogen get another lone pair? No, it cannot. All right, so no lone pairs on the hydrogen. So I had to put that 12, set of electrons there, or the last 2 electrons as a double bond. All right, so what does that do for me? Well, again, because what's true for this carbon is true for that carbon, I got 3 electron groups. I got 1, 2, 3. I can use my right hand one. 1, 2, 3 electron groups. There's no lone pairs. If you're dealing with carbon, that should always be 0. So what is the shape of this going to be? It is, whoa, things are going crazy here. Hang on. The shape is trigonoplanar. It is really nicely symmetrical. It is nonpolar, and it is nonpolar. All right, I want to do one more with you. I know I'm kind of talking a long time here. I'm going to do one more with you on the next page, okay? So let's go to the next page. And I want to do this, all right? So if you were to start off, carbon is a central atom, as is oxygen. All right, so go ahead and put out the rest of your hydrogens around here. So I have hydrogen here, hydrogen here, hydrogen here. Now what? I need to add up all my electrons. So I have 4 plus 3 is 7, plus 6 is 13, plus 1 is 14. So I have 14 electrons. I get 2, 4, 6, 8, 10. I need to add some more electrons. So here's 12, here's 14. So does that fulfill everything I've taught you so far? The answer is yes. Carbon has no lone pairs and oxygen has 2 lone pairs. Life is good, okay? But now what? I have 2 central atoms that are not the same. So I need to split this up and do this for each central atom. So how many electron groups does this central atom right here have? It has 4. How many lone pairs does carbon have? None. What is the base shape of carbon? Well, what's 4 and 0? Go back and look at the front page there. It is tetrahedral, okay? So what about the symmetry? It is symmetrical. There's no lone pairs. However, you can look at it this way. What about the bonds? Well, these bonds are nonpolar. But what about the other bond? What about the C and the O bond? All right. It is also, well, it's not also nonpolar. It's also polar. All right. So I have 3 nonpolars bond, but I do have a polar bond. All right, well, let's keep going. What about the next one? Look at oxygen. How many electron groups does oxygen have? 1, 2, 3, 4. It has 4 electron groups. How many of them are lone pairs? I got 2 of them. So you remember what that shape is if you start off as a tetrahedral and remove 2 bonds and replace them with lone pairs? It's bent. What did I say bent always was? Not symmetrical. What about my bonds? Both bonds are polar. This is a polar bond and this is a polar bond, so I'm all set. So what is going to determine this entire molecule? The fact that I have one set that is not polar, or that is not symmetrical and polar. It has, this is my requirements of being polar. My entire molecule is polar. So even though this area here is non-polar, the fact I have the O right here makes the entire molecule polar, and structure determines function. Okay, so I'm going to leave you here. I know this was one of my lengthier videos. I apologize for that, but hopefully it was a good review for what you should have learned in your first year chemistry class. So don't wait to be great. We'll see you next time. Bye-bye, everyone.